without further ado, I'm really excited to introduce our first presenter tonight. We have a couple of folks joining us from the city of Edmonton. So please provide a Zoom welcome with a nod of approval, a smile, a head. Right from city of Edmonton, a little bit about ML and the MLRT. Take it away.
Hi there. I just noticed there's a bit of a lag on my computer here, so I might turn off the video if someone wants to give me a signal if it's not working or not. But I'll start with an introduction. My name is Craig McKeown, and with me we have Rajiur, also from the city of Edmonton. So my role with the city is the director of the LRT operations and maintenance. And so what we're going to talk about today is the LRT and a little bit about analytics and what we're doing to advance. So just looking at the screen here, seeing if is the presentation being shared by any chance? How about Warren? Are you able to see the presentation?
No. Are you sharing?
I believe Rajiur is going to be sharing the presentation as we go through a few slides here. We rehearsed this yesterday and it worked out really well. So apologies for it not going as slick as it did in the rehearsal. Well, I'll tell you what, I'll just keep going through it and then hopefully Rajiur is able to share the presentation. If it's not up by my second or third slide, then I'll share it and we'll go from there. So the first slide that I have is just a bit of an org chart just to show you where we fit in the organization. So Edmonton Transit is a part of city operations, which is part of the city of Edmonton. And then our role is within Edmonton Transit, and we run the LRT operations. So that's everything from maintaining the track structure, all of the LRT stations, the transit centers, all of the overhead catenary, substations, the trains themselves. So just about anything to do with the running and providing the service to the public. And so really what we're all about is providing the best service we possibly can to our public. And so what we're trying to do is leverage the power of data to help make our service better, faster, safer, more efficient, and really just making it as the #1 transportation option. So I just noticed that looks like Rajiur, who's be sharing our presentation, looks like he might have got kicked out of the room here. So what I'll do is I'm going to try to share the presentation myself here. Sorry about this. Something's up.
No worries. We all know the trials and tribulations that come along with the virtual presentation. So please, thanks for bearing with us. And we'll get this up there. Like Redder's maybe back in now. All right, that looks great.
Okay. So how's this? Are we up and running so far? Okay, so thumbs up. We'll keep going. Now we're cooking with gas. Okay, so automation mileage program, something that we kicked off using and leveraging data. So really throughout this presentation, what I'll talk about is a little bit higher level, and then Rajiur is going to get into more of the technical details on how exactly we leverage this data. So for those who aren't in Edmonton or aren't aware, but Edmonton's LRT system is actually the oldest light rail system in North America, which we take a bunch of pride in. So it was built and first commissioned back in 1978 for the Commonwealth Games. And so we have some of the oldest trains and the oldest system up and running. And along with that, we also had some old processes that had just kind of stuck around. One of them is how we do our vehicle maintenance. And so what we did is we really rely heavily on the mileage. So similar to your car, when you take it in every 10,000 kilometers or 6,000 kilometers or whatever, we do the same thing with the trains. So every 10,000 kilometers, we do a number 1 inspection, and then we have a system after that. And so how we take that mileage is a human physically crawls under the vehicle every day after it gets back to the barn and reads what's on that slide there. So you see one of those odometers, kind of wipes off the dirt, reads the odometer, writes it down on a piece of paper, hands it to another fellow who takes that number and physically types it into a computer to upload it into our ERP system. And then from there, we use that to help schedule, okay, well, which trains need to stay back, which ones go out for service, and so on. So it's really a manual process. It's labor intensive, it's inefficient. There's multiple different areas where humans can just make an honest mistake, write down a number wrong, something like that. So that's what we've been doing for about 42 years until Rajiur came along and helped us out leveraging data. So I'm just jumping to the next slide here. So what we did was we took our signal system and it figured out where the train is. And we're going to dive into it in a little bit more detail in a couple future slides. But we ended up automating that entire process. So the train comes into the shop, it uploads automatically based on where the signal system has figured out where the train is, where it stops at each station. It calculates the distance between when that train leaves the yard and gets onto the main line, calculates all of that, and then uploads it automatically into SAP, completely eliminating the entire process of having that human go underneath the train and write down that mileage. And there's all sorts of possibilities for near misses between the operator and the person recording that mileage and so on. So we've completely automated that. And so right now it just happens automatically. And so the objective here was to make it reliable and consistent without human intervention. And then use our existing system without any modifications and no adverse effects to our operations, which is something that we ended up achieving. And we've been running this now for about a year. So this is talk a little bit about the signal system, how that works. And what we have right now is a bit of both of these. We have a traditional signal system where we have physical limitations where trains are physically separated by a certain distance. And then we also have in a certain area a communication-based train control system. So the trains essentially speak to an overall computer who monitors where they are and keeps the trains appropriately spaced apart. Those all feed into a computer that essentially tracks where those trains are, and we leverage that data to calculate the mileage. So this is what the control system looks like, or sorry, the control room looks like. So those boards that you see above you there on the top screen, you'll see little icons where the trains are, where they move to and from. And there's little icons for stations. And so then we'll have anywhere from 2 to 4 people in the control room at all times, monitoring the train movements and the routes. If there's any sort of issues, single tracking around and making sure that, all the trains are leaving on time and schedules and stuff like that. So this interface is one of the resources that we took to input into this mileage program. And this is essentially how it works, is it takes our ATS, which is the automatic train supervision, and essentially puts it into a database. And then from that database, that's where a number of scripts were developed to start calculating, okay, well, where did the train go? How far did it go? How many stations did it go? Which vehicles were in that train consist? There's a bit of a double check process we have in there. And then this is the database that we pull from. And there's a whole pile of challenges. I believe this is the slide where Rajiur is going to take over, but what I will pass on before we kind of go through this busy slide is one of the interesting stories that we discovered throughout this project. The odometers, some of them are old, and in a couple cases, we're only calculating mileage in one direction. So picture a train driving one way, calculating the mileage on the odometer, but then not calculating the mileage going the other way. And so after these scripts started to take action, we started to notice, that's interesting. Some of these trains are showing double the mileage on our new scripts versus what is showing on the odometers. And after inspection on the odometer, realize it's only calculating it on one way. So that means that those trains for a period of time were only getting half the amount of inspections that they should have been. So really this project improve the accuracy of some of the maintenance that we're doing. So it was a bit of an aha moment. We're like, this is interesting. How long has this been going on for, and how many inspections may have gotten missed? But again, it's the power of data and being able to calculate automatically rather than relying on mechanical devices or human errors. So I'll just double check. Rajiur, are you ready to take over here? Are you back in?
Yeah, Craig, I'm back.
Okay,
yeah, sorry,
perfect.
actually some internet issue, I guess. Sorry for that.
It wouldn't be a good. It wouldn't be a proper
okay
Zoom. Yeah, no, I just wanted to say it wouldn't be a proper Zoom meeting if we didn't have someone talking while on mute, or someone getting kicked out of the meeting, or some sort of error. So I think we're up and running now. So I'll hand it off to you to take it from here, and just let me know when we want you to click next slide, and we'll go.
Okay, that sounds great. Thank you. Thanks, Craig. When we started this project, we had a lot of challenges. Here we listed some of them that we have faced. So I'll go through these challenges, and then throughout the slides, we will discuss about how we have come with different solutions. So one of the challenges that we have faced was LRT uses separate network, and we have to transfer the data to the corporate network where we are doing all the processing. And also the data size was another concern, that it has to be in a certain sizes that we can easily sustainably transfer those data. And as Craig mentioned on one of his slides, that when we start this project, one of the constraint was that there will be no negative impact on the current system, so that we will not compromise the existing signaling system. So we have to make sure that our new processes will not impact anything in a negative way. And as I said, that the script was deployed in the corporate server, what we call this agent server, that is controlled by the data engineering group. So at the beginning, like, we have some challenges that we don't have access to that agent server. So when we make changes, we cannot test those scripts, that how it's impacting until it's going to the live. So we need to make sure that there is a way that we can do the testing before we deploy it to the agent server. Other things that that come across the project, that when we start, it was small, and we are adding more features to it, and then we figured out that there is a requirement for the version control, and we did not know that how we can manage the version control. So we get a solutions at the end, but at the beginning it was a challenge. And City of Edmonton is a big organization, and we have to work with different stakeholders. So we work with the enterprise resource planning group. We have to work with data engineering team. So we need to make sure that we are communicating properly, and it was a challenge at the time. Throughout the project, we have integrated multiple platforms. So we pull the data from LRT database and then move it to different network, and then we transfer it to the corporate network, and then we use those data, and also we integrate Tableau to visualize those data in a nice presentable way. One of the biggest error that we have found here is, like, when we were looking on those data, as Craig showed in the previous slide, that there was data coming from the vehicle. So VOVC is sending the signal to the ATS, and from ATS we get this data. So every train it consists of, like, like several cars. And in this mileage project, what we are doing is like we are calculating like how many times those trains are moved the line, and we need to know what is the car belongs to that particular train. So sometimes those VOVC that's located in the vehicle may not communicate to the ATS, and then if it does not communicate, then we don't know what car belongs to that particular train. So we need to make sure that we have those informations. So so we use another database to get those car information for the vehicle. So yeah, next, can you move next slide, please? Um, so here, here are some ATS event. So those are the signaling incidents that register in the database. So train arriving to the stations, train departing to the stations, any signal changes become red to green, green to red, or train mandatory brake. So mandatory brake is like when train stops all of a sudden for some particular reasons. So all those data are storing in the ATS, in the signaling system, and we use those data to figure it out, the mileage for those particular vehicles. So those are the data input for our program. And if you move to the next one. So that was at the beginning, that was our proposed solution, that how we can transfer the data to from LRT network to the corporate network. And we find out if we put a secured FTP folder, and then a technical service group in LRT actually help us to transfer those data to that SFTP folder. And from SFTP folder, we put our script in the corporate network, and corporate network can communicate to that SFTP folder. And from there, we transfer those data and process all those data in the corporate network. And then we do all our visualizations from there. So at the beginning, what we did a proof of concept test. So what we did is like we go to the signaling system backup server and plug in a USB and get the log that we are required, and then we put it in our put it in a laptop where we deployed all these scripts, and then we run those things. So we did those test run for almost a month, and then we validate those data with because at the same time we are running the mileage program parallelly to the manual program was running parallelly. So we compared those data and validate that is there any error, and we did that for a month, and then after that, we are satisfied that the error was within the range that is acceptable, and that can be deployed in the next stage.
And when he says, when Rajur's talking about the error, we're talking, I believe in most cases, it was within 1%. So the scripts and the calculation model of calculating how far each car in each consist is moving, simply using the data from the signal system was getting within 1% of what the odometer readings were getting. Other than those error cases where it was 100% off, in which case the odometers were broken, and the calculated model was the one that was accurate.
So the proof of concept was like it's pretty easy to make the changes whatever we need to do, and it's like initial tuning process, and it's one of the things, like we have to plug in a USB in the signaling backup server, and then it's a very manual process. And it has this inbuilt security issue because we have to plug in the USB in the signaling system, which may cause some, bring some viruses. And the process was not sustainable. So we proposed, we developed more sustainable solutions, and which I'll show you the next slide. Uh, so what we did is, in the LRT network, in the backup server, we deployed some batch scripts, and which run in the morning, and then which transfer the log, signal log, that ATS log that I showed previously, to the SFTP folder. And from SFTP folder, we have other batch program in the agent server, which grab those files, and then it process in that agent server, and then it transfer all those files to a particular locations. And I'll show more details in the next slides. It will show the whole data flow of our system. So the way all those events are working is like at 3 a.m. The DLG log, that means the log that we use to calculate our mileage, are moved to the backup server. And from that backup server, it moves to the SFTP folder, and from SFTP folder, it goes to the corporate agent server. And so we need a different source of data. So one source is the signaling system, and other source is LRT database. So as I mentioned, that sometime ATS does not have the card information. So we need to get the card information, and those card information we capture is from the LRT database. LRT database actually records all the activities, and it is like in the previous slide, Craig showed you a big picture that the control room. So the controller actually regularly inputting the activities in the LRT database. So whenever a new train come in line, they enter all those things in the database. So we use those data to validate, to calculate in combination with the signal data. And then based on these two data, we find out the right car informations. And from there, we calculate the mileage for each different vehicles.
This I thought was a cool, sorry, I don't mean to interrupt, but I thought this was a cool discovery. As the project was evolving, we had this, all of our control room staff will enter in the vehicle numbers, whether the A end or B end is facing north or south, who's driving that specific vehicle. We log all of that information. And so then that was used then as a backup in case there was any data issue from the ATS or the signal system. Then the scripts would double check with that human input as well. And so then combining those two together and verifying that information to double check, oh, was there a typo in manual? Or if the ATS was missing something, well, we could go and then pull that information, extract it from the manual. So it's a bit about double check process to make sure that we had everything.
Yeah, thanks, Craig. So the final system was like fully autonomous. It's like no human input here. So it's like completely happening in the background, and logs are already processed in the morning, and is no security risk. And this is like, if there is something happen, like if we see that log is not processed, so we have a script that can tell us that where is the problem, so we can easily troubleshoot those problems. So it was a pretty sustainable solutions. In the next slide, we'll see. So in the challenges that I mentioned, that we were struggling, that how we can manage the version control. And the data engineering team actually did support us here, and they provide us like account with a GitLab. And we are using GitLab to do all those version control. And And if there is like, it's really very useful tool that like whenever we make changes, we have all those records, and if we find out that the changes is not effective, we can go back easily with this tool. So that was a great input from our data engineering team. In the next slide, we'll show like what are the different uses of those data that we are collecting. So from the signal data, once we processed, we can calculate the delay of the train. So it compares the schedule and what happened, the actual incident. And from there, we can show like when those delay happen, what time of the day, which stations, all those things. And we haven't calculated like, is there any particular day that we will see lots of delays happening? So that we can go deeper. So this is one of the report that we have. In the next slide, we have, it shows in the map that where those delays happening, and it can segregate by hours, by locations. We can dig deeper. Dwell time is another important measure in the railway industry. Is like how long trains stay in a particular stations. So we calculate that as well. So we have some benchmarking. So we look on that. If it goes above that time, we can look on that and do some investigation of why these things happened. Then we runtime analysis is pretty important. Like it's like the time required between two stations, and this is used as the input for a schedule. So we got a lot of data to figure it out, like what is the optimum run time, and from this data we can utilize the runtime to optimize our schedule. Then in the next slide, we'll have a mandatory break data. So sometimes, like if you are traveling through LRT, you may see that all of a sudden the train just stopped. So those are mandatory break. So we need to know those events, and we need to figure it out why those events happened. So from this data, we actually look on those data that what is the cause of those events. So we can look on those deeper, and we can see that which location those particular events happen, or is there any significance with locations, any significance with different vehicles, all those things. So we can calculate, we can analyze those data by using this information. And finally, mileage, as I said, that mileage is used to do the preventive maintenance for the vehicle. So this is where it shows in the shop utilize these tools. So they look on those chart and then see which vehicle will go to the scheduled maintenance next. So they utilize those informations on a regular basis. So we give them this is a output of our program. I think, yeah, that's the last one. So throughout the project, CPC is a consultant to ETS, which is UK-based firm. So they help us throughout the project. So it's great thanks for their support throughout the project. Besides, City of Edmonton data engineering team also help us a lot on that project, and other groups from ETS are also involved in this project. And then I would like to thank Amii for giving us the opportunity to present in this platform. It was a really great opportunity, and thanks for that.
Really appreciate your time. This is like the very beginning of how we're going to be leveraging data. So for everyone in Edmonton, I'm going to assume that you love to use the LRT. And so what you're going to notice, hopefully in the next year or so, is it becoming increasingly more efficient and more reliable based on leveraging this data. So it started with this mileage project, and we were able to save essentially a full-time position of someone who would walk around and check the mileage and write it down. We've completely eliminated that task, and then we've redeployed that person. In today's day and age, that person is now cleaning the vehicles. We have a very rigorous cleaning and disinfecting process throughout the trains and stations. But we're able to reallocate that labor resource based on leveraging this data. And so we look at that as saving taxpayer dollars. But that's just the beginning. Like, so Rajiur went through a few other things that we're able to do, but it doesn't stop there. We want to look at that to start figuring, okay, well, how can we start predicting when things are going to fail, component failures, and replacing them before they start failing? You know, can we look at the speed limits? Does it make sense to slow things down? Similar to when you're driving a vehicle and you see in the distance the light turned red. Well, you're going to naturally slow down and wait for it to turn green before you start hitting the gas again. We want to start looking at those things as well. Can we start adjusting our speed profiles and maybe start making it more efficient and save energy? So there's just a mountain of things that we can do with this data. We're changing our signal system, which doesn't change any of this intent. It ultimately just changes the brand of the input, but the overall process on everything that we're doing with this is all going to remain the same as far as storing that data and then analyzing it. And so as this project unfolded and as we continue to kind of go down that path of analyzing data and leveraging it and starting to hit some successes, that's when the discussions with Amii took place to start to say, like, hey, these are some of the things we're doing. What can we do to work together? And that's what spawned us here today to talk about it. So anyway, just want to, before I continue to keep rambling, just want to say thanks again. Really appreciate it. And yeah, happy to chat LRT all day long if you want.
Hey, thank you so much. This has been fantastic. We're already getting some questions coming into the chat. And obviously, you know, really important work happening here, and you know, beneficial to everyone who's taking that train, relying on it to get where they need to go. So for anyone who has put a question in the chat as well, I just want to say, feel free to unmute yourself and ask. Just pop in here and read off the first question for you. So were there any other inputs besides mileage that were used for the preventative maintenance algorithm?
So that's one we're still working on. So previously, not really. So it evolved over time. So if I understand the question correctly, in our preventative maintenance program, what we're looking for in the future is much more than just mileage data. The LRT trains have tons of sensors, and there is a whole pile of information that we can gather and analyze. And so what we plan on doing with that preventative maintenance, and we have a list of about 30 or 40 different items that we look for. So, you know, does the track brake apply, you know, at speeds greater than 6 kilometers an hour? That would signal something to us that there could be something that we need to look at. And so using the mountains of sensors and all of the different data, we've started with a list of about 30 or 40 items that we're going to be checking for, which would indicate us that, yes, we need to start doing something prior to seeing a failure. But then we want to start looking at AI to start finding patterns that we don't know exist. So let me know if that answered the question.
That's great. And also, I will just reiterate, you now have the ability to, should you wish to ask a question. Thanks for bearing with us. I'm just learning here of some of our additional kind of security measures for tonight. So we want to make sure we have these run as smoothly as we can, but you now have the ability to unmute yourself. So if you do want to jump in and ask a question, please feel free.
Hi there, it's Neil. I work for a company called NetApp. I would just be curious to know how much data you are generating on a daily basis. Are you archiving this? How long are you keeping the data sets? Can you answer those questions?
I can't. I know it's a lot, but I think what you're looking for is probably a metric. I'd probably defer to Rajiur. Hopefully he'll be able to answer that one.
We are generating, I don't know exact size, but yeah, we are recording all those data in a database. So if you see one of the slides, we show that discovery zone database. So we have a dedicated database, and we have different tables created for different types of data. So we are recording all those data there. Yeah.
And it's very.
And are you? Sorry, are you creating a? Sorry, are you creating a data lake and just maintaining that, you know, within? I see you're using Google Drive there. Is that, you know, where you're storing a lot of this information on an ongoing basis?
I would not say data lake yet. Is still as a database that we use this database to visualize the data. So we connect Tableau with this database, and we utilize those data in Tableau for visualization purpose. For Google Sheet, there are other groups inside ETS, like LRT engineering group. So they develop tools using Google Sheet, and we inputted our data to that Google Sheets, so that they can capitalize the data with the new updates, new informations. So yeah.
I understand. Thank you.
Yeah, thanks for your question.
Awesome. We've got time for one more quick question here, if anyone wants to take advantage of it. All right, well, I'll read the last one here. So it says, I noticed the use of scripts for the mileage project. Did your team consider other approaches to test your solution? For example, use of simulator software or digital twin for scenario analysis?
I'll try to answer that first, and Rajiur might be able to elaborate. We did. So one of the things that was important to me in the management role was to try to keep costs down. So we didn't have a strong simulator available to us. So what we tried to do was build this ground up to see, is this going to work using existing resources, and are we going to notice any benefits, and can we do this for free rather than buying a simulator or renting or leasing or whatever it would take. So we tried to do it organically and starting bottom up rather than investing in an expensive software.
Sorry, do you mind if I ask one more question? You know, what were the business benefits and the, you know, based on the outcomes of this project, you know, how much can you quantify what the city saved in terms of, you know, finances, in terms of soft costs? I'd be curious to see, you know, what kind of business outcomes you got because you went through this project successfully.
Yeah, so this is really just the start. We haven't gone through the process of quantifying the cost savings yet. I think that's going to be something that we want to do in the future. Now, this has only been live for about a year. And the obvious one is the extra resource in our maintenance team. So we launched this, and then about 4 or 5 months later, the pandemic hit, and costs kind of went all over the place as far as, you know, drastically increased in terms of our cleaning costs, and then our service changed and everything like that. So it got a little bit muddy as far as overall cost saving. But what I would say is the very obvious benefit was we saved a full-time resource and was able to redeploy that person simply just from this portion of the project. But what I'd like to do is move down the path a little bit further and kind of explore other opportunities for benefit. And then we would go through that exercise of calculating and quantifying what those cost benefits are, if and when we need, you know, to build a business case to invest public dollars in something further. So I'd say that's on our horizon, but I don't have a strong quantifiable number for you today.
That's fair. I think you've been able to establish some benefits for sure. I think an FTE is huge, actually. So well done. Thank you.
Yeah, that's fantastic. We're excited to have you back again in when you've started to go down some of those roads a bit further as well. So that's really exciting. So much, and please join us in thanking our friends from the city for joining us and sharing this with us today. This has been fantastic. Excellent. Applause, great. Thank you. And so one of the things that we like to do in between these talks is to create a chance for anyone who's you can unmute, you're more than welcome to unmute, and we can take 30 seconds. You also put out there. Maybe you're looking to hire someone, share a win. Please feel free to take advantage and use that time. I'll throw on my commitment to paste the Startup TNT info in the chat as well, so you'll see that just briefly. But if anyone wants to take advantage of this 30 seconds, the floor is yours. And if not, then I will provide a shameless plug for us here. We're actually hiring some really interesting positions at Amii right now. So we have a machine learning scientist role available and several program scientist roles as well. So you can find those on indeed.ca with a quick search for Amii. So please check those out if you're someone that's looking to do some really interesting work in the field. We have a fantastic team to work with, interesting clients, and really interesting work to sink your teeth into. So we'll look from you. And for our next, this is one that I've been really excited about, a familiar face from around a lot of the major AI conferences and a lot of these monthly meetups and events that go on. So our final topic of the year for the series of our AI meetup is a good friend of ours, Pam from MDA, who's going to be talking about his favorite topic over the holidays, AI in space. Please take it away.
Okay, thank you, Warren, and thank you, Zavon, for inviting me. I'm happy to present. Let me just share. Hopefully everything goes smoothly. Can you see my screen? Okay. Yeah, so I was showing these slides to a friend of mine just to get her feedback. And the first question she asked me is, why do we want to send aluminum to space? And I realized the font is a little bit strange, but so I'm going to talk about AI in space and not aluminum. So yeah, I'm a research scientist at MDA. So we work on different things, and I'm going to talk to you about AI in space, just to maybe clarify a little bit. So this is sort of a grandiose title, so I don't claim to sort of cover all the applications of AI in space. So I'm going to give you my perspective from what I've seen and what MDA has been working on, and hopefully get you to think about some of the applications of your AI research and the work that you're doing, and maybe bring it to us and try to establish collaborations or future work together. So I'll start by giving a very quick overview of MDA for those of you who might not know what MDA is. I'll try to highlight some of the problems in space and why I think, or many people think, that AI and ML could contribute to solving some of those problems. So the main technical content of the talk will be two topics. So one is the results of a recent publication we had, which aimed at detecting and classifying RSOs. So these are resident space objects, an example of which is a satellite. So we had a paper trying to do that. And finally, there's an ongoing work of you're trying to develop a real-time image synthesis tool, or think of it as a simulator, which I'm hoping we could use down the line to do some interesting reinforcement learning or some of the other things that the people at Amii might be very interested in. So I'm excited to get your feedback on it, and then I'll conclude. Okay, just a quick summary of MDA. So we've been around since 1969. Most of that time, we've been a Canadian company. I think on 2 occasions we became a US company, but then we came back. So currently we are a Canadian company. So we build satellites, we operate them, and we also do, we have an AI lab within MDA in Richmond, and we do a lot of AI work. So some of the, so you will hear about some of the specific satellites that we do, that we sort of designed and work with. But you've heard of the Canadarm program. So the Canadarm 1 and 2 was built by MDA, and Canadarm 3 is going to be built with some help from Amii as well. And RadarSat constellation. So these are SAR satellites that have been built and operated by MDA. Yeah, so I'll get into some more of these details. So currently there are 3 branches. There is the geointelligence branch, there is the robotics and space operation branch, and there is the satellite systems. So I am from the geointelligence branch, so we are located in Vancouver, BC. So I know there is a formal collaboration between Amii Innovates and our Brampton colleagues who are focused on robotics in space. So I'll mention a few things about that, but for the most of this part, I'm giving you a geointelligence perspective, which hopefully will make sense in a minute. So I will also advertise some positions and jobs at the end. So I just want to give you an idea of what are all the locations in case you're interested in applying. So like I said, I'm from Richmond, which is in Vancouver on the West Coast. And then we have 4 locations on the East Coast. So our headquarters is Brampton, and that's where they do all the space robotics stuff. Okay, so before I go on to my talk, I just wanted to mention the exciting new data set that's becoming available. So this has come about from a collaboration with Amii. So it's called the Trail Dataset, Training AI Laboratory. So this is a lab set up in Brampton office, and the purpose of it is to generate realistic data so that we can try different AI algorithms on it. So I'll tell you a little bit more about the data. So this is from the Canadarm2, and the hope is that we're going to be able to use this data for training Canadarm3 algorithms. So this is going to be a Kaggle competition. So the purpose of the data is to investigate collision avoidance. So this is the collision between the robotic arm and whatever it's operating on. So it's going to be eventually mounted on at the lunar gateway. So you'll need to basically, we don't want it to collide with anything. So the data will consist of 10 scene cameras. So there's 1 robot mounted on the camera. And as I mentioned, the goal is to detect when the robot is within some threshold, in this case, 30 centimeter of the obstacle. And so it will be, so you can search for it in Kaggle using those keywords, or you can get in touch with me and I can give you the link to where the data set is located right now. Okay, so going back to geointelligence. So to sort of differentiate between what we do at Richmond and what the Brampton team does. So we are sort of more focused on the satellites and other space objects. So here is just to give you an idea of the scale of the different satellites that different people operate. So you can see it. It can range anywhere from a large satellite, which could be larger than 1,000 kilograms. So I would say most of MDA satellites fall in that range. RadarSat-2, RCM, and Sapphires. All of those are large satellites. But there's a trend going on towards building and launching smaller and smaller satellite, but in larger quantities. So you can see on the bottom figures how small can these things get. So that's the CubeSat. So it's 10 centimeters by 10 centimeters by 10 centimeters is a unit of CubeSat. And you can see, so of course, you won't be able to fit in fancy equipment and sensors that are as good as the ones that you can fit on a large satellite. So the point is, so this is one of the areas where AI can potentially help out a lot. As I'll hopefully highlight through our work here as well, that you don't have the luxury of all the data processing that you would normally do on a big satellite. And so this is one of the areas of opportunity. Okay, so that was a general satellite. So for Canada, so there are 57 Canadian satellite assets currently in orbit. That number might have gone up. So this is, I think, a year old. So there's a bunch of applications: communication, search and rescue. There is space surveillance, maritime surveillance, Earth observation, and scientific purposes. So some of the things that I can highlight is the bottom right figure is the RCM RadarSat Constellation mission, which is a series of 3 satellites that MDA launched last June. So it's operated by the Canadian government. And the top right is another satellite that's currently it was built by MDA and it's being operated by MDA for the Canadian government. It's called Sapphire. And its job is to keep an eye on other Canadian satellites and other assets to make sure they're safe. So all the data that I will show you today is from Sapphire. Okay, so before I get into the technical details, I just wanted to sort of give you some subset of things that AI, I think, could help in space. So some of the bigger applications are detection and mitigation of collisions. So these collisions could be, like I showed you previously, it could be the robotic arm not colliding with anything, but also it could be, we don't want the satellites to collide with debris, which I'll get to in a second. So there's a lot of that going around Earth right now. We want to automate we want autonomous or semi-autonomous tasking and scheduling of satellites. I should mention that autonomous does not equal intelligence. It could be, there doesn't have to be any learning going on. So it could be completely automated using, let's say, control algorithms. But we'll get back to that in a second. Detection and classification of satellite maneuvers, detection classification of these satellites themselves. And so once you take care of the perception, which arguably is probably where AI technology are the most mature, and you want to figure out what course of action to take. There's usually a large communication lag between the satellites and the operators. And if something quickly happens, usually it ends in catastrophe at the moment because everything is manually operated. So ideally, we want some autonomous sort of capability within a satellite to be able to handle some situations. So the three that are highlighted in green, so these are some of the projects we have been running at MDA at different stages in R&D mostly, but so I'll show you some of those. I'll share with you some of the progress we've made so far. And so some of the things, specifically the simulator I mentioned towards the end of the talk, tries to address those highlighted in yellow. So the paper we published is specifically focused on detection and classification of RSOs, which is a simple application. We just wanted to show that it's feasible, and so I'll share that with you next. Okay, so just wanted to show you these pictures. These are kind of outdated, but I think there's really no point showing beyond 2015 because you can't see Earth anymore. So 1957, there are no satellites. But you can see this is the amount of debris that's been collecting in the low Earth orbit around Earth. So this is the motivation of why you need AI or any sort of technologies to avoid colliding with these things. And just to give you an idea, this is what happens when you collide. So that's a 4-inch thick piece of aluminum that's hit by 1-inch plastic at 15,200 miles per hour, and that's what happens to it. And imagine there is thousands and thousands of these 1-inch pieces flying around Earth, and you want to make sure your satellite is protected. So I came across this term, the Kessler syndrome, which is the idea that if you have one of these collisions, it creates more debris. That's basically creates a cascading effect of debris that eventually you're not going to be able to launch any more satellites because it's impossible to keep them safe. Okay, so just to give you an idea of what kind of data we're looking at, so focusing on the left side, so this is an inverted image of a typical image you collect from Sapphire. So you notice these, let me just show. So these 4 circles, so 2 of them are very close together, but then there's 4 of them. So these are cluster of satellites called Anik cluster. So these are telecommunication satellites. That's one of the things that Sapphire is tasked with keeping an eye on to make sure they're functional. So the reason there are circles in this image is that they are in a geostationary orbit. So relative to the Sapphire, they're not moving. So you see them as circles. And everything else that you see as these long streaks are the stars. And because the exposure is not 0, so by the time as you're collecting, you're seeing the frame move. So you see them as streaks. And then different thicknesses basically means different brightnesses. And then you also notice all these sort of little dots. So some of them are just defects of the sensor. And some of them are just radiation strikes because you get radiation from different sources hitting your CCD sensor. And so we need to be able to deal with that. So I'll get back to, our entire sort of processing is focused on dealing with images like that. So let me show you, so another sort of data. So this is an actual image. So I just wanted to show you what some of these images look like. So these are 2 of these Anik clusters. So these are like sort of these I don't know which one is which, but the center one is ANIC F1, which is the brighter one, and then the other one is ANIC G1. And as you can see, they are sort of rotating in a three-dimensional space around each other. So in some cases, they overlap and then they separate. So one of the things that you need to be able to figure out is which one is which. So you might think it's easy because one of them is brighter, but that brightness depends on what we call the phase angle, which is what is the angle of the sun hitting it at that given moment. So one of the problems that we would like to be able to solve is to do the conjunction resolution, figure out which one was which. So this is just to give you an idea of what these things do. Okay, so going to our papers. So what we wanted to do is to detect and classify some of these satellites in images that are similar to the one I showed you in the last slide. So obviously, this is a pretty well-posed problem in AI now. It's just supervised classification. We did try a bunch of different classifiers. Eventually, we discovered that deep neural networks were the best. So again, just to motivate a little bit some of the challenges. So on the top left is a clean image. So that's the kind of thing we would like to see. On the top right, so it's an image collected over South Atlantic. There's a lot of radiation strikes, as you can see, is this sort of noisy background, which sort of pollutes the image. Here you see stray light contamination just from a reflection off of some metal surface hitting the CCD. So it basically makes all this data kind of useless unless you process it. And then finally, you would like to be able to filter all these out to be able to process the image. So what we wanted to do was, as a first step, so we had two goals. One is to basically classify, which I'll go through in a second. And the second goal was to put this in an onboard processing unit. So obviously we won't have access to AWS in space. So what we want to do, we want to be able to put it on some kind of onboard processor, which I'll get to in a second. So the 5 classes we wanted to classify as RSOs: stars, stray light, dark current defect, and transient radiation defects. So this is sort of the size of the data set eventually we were able to put together. And we went through all the typical conventional things you do about train val test split. So all the data, so this is just a prototype. We could potentially put together a much larger data set if needed. This is just a proof of concept. So this was collected over just one day of Sapphire operation. So one of the things we did just to save our analysts some trouble labeling is, so we have a small subset of the images available labeled manually. We trained a smaller, simpler classifier, used it to pseudo label more images and then correct it, and then do this a bunch of times. Eventually you end up with a big data set. So as you can see, our models are pretty simple. So we even started with a very, very simple one with just a fully connected layer. And then we just went into slightly more complicated. So the details of our work is published in that paper. If you can't access it, just contact me and I'll send you. There's a lot more detail that in the paper that I have time to share here. But if you're interested, just let me know. Okay, so as I mentioned, if you remember in the beginning, so there is a trend to going towards smaller and smaller satellites. So you might think that, okay, why not put a large ResNet 50 on board and just have it give you 100% accuracy? So we wanted to see what is the smallest network we can put on board, and at the same time deal with bad optics. So Sapphire is a multi-million-dollar sort of equipment, and it does have pretty good resolution, and it has way better resolution that you would expect to have in a CubeSat or something small. So one of the things we wanted to see is if you add increasing levels of artificial noise to the images, how do you trade off between the complexity of the networks and the performance that they have? So you can see some examples. So this is the largest amount of noise. So you can see in some cases, you really can't tell that this is a stray light. So this is like severe amount of noise. Like even humans can't tell the difference. So we wanted to basically investigate this. So here is some of the results. So these are confusion matrices. So basically you want to see everything in a diagonal, meaning that everything was classified correctly. So as you can see, as you increase the amount of noise, then it starts getting worse and worse. So you get a whole bunch of non-diagonal elements. And depending on what object you're looking at, for example, the defects and radiations are kind of roundish objects. So that's why they get confused a lot more often. So there's nothing surprising here. You add more noise, you get worse performance. And perhaps not so surprising, the CNNs do better than fully connected layers. They're more robust to noise. So one thing we figured out, we realized, is that once you make the models more complex, so if you go to a larger number of layers, you're able to recover some of the performance that you lose because of the noise. So so I won't go through all the details of all the results here, but so for example, if you compare the last column, which is our most complex sort of network we use, this is equivalent performance to the noise being half of that, which is substantial amount. So you're able to learn how to detect signal through a lot more noise if you use a more complex model, even though it doesn't really help you with the simpler cases. Okay, and so this is another goal that we had. So we wanted to investigate, okay, what does it take to put these networks into these different kinds of sort of neural net accelerators and inference engines that are designed to work in low power. So we looked at several options. You can look at the paper again. So these are, I should mention that to put these into space, you need them to be radiation hardened, which these are not. So that basically means if you put a GPU into space, it's going to be struck by radiation, and that's going to flip bits randomly, and that could severely degrade the performance of your inference. So there are ways of dealing with it, but these are not radiation hardened yet at this stage. So we focus on the NVIDIA Jetson Xavier. So the reason we focus on that, because it allowed configuration of the power output. It could use GPUs as well as other accelerators, and it was also able to do low precision operations. So this is just some of the highlight of some of the results from the paper. So a couple of things I'll point out that might be interesting. So the fully connected layers, you can see, so this is the throughput. So this is the amount of images per second. So the fully connected layers somehow were much higher throughput without any, so this is without any optimization. And then, so you can see also with the amount of power, the more power you give it, the higher the throughput. But of course, this power is one of the things you want to minimize when you want to put something in a satellite, because you have limited amounts of it. So after kernel optimization, which is one of the things we did, so we did a bunch of different types of optimization. After this one, you can see the throughput substantially increased by quite a bit in both. I think this is for the largest model that we have. And yeah, so both throughput and efficiency increased substantially. Okay, so notice I talked about classification. I didn't mention anything about detection. So usually you need to have like some kind of object detector, and then once you have your chips, you can do classification. So I didn't talk about that. So so currently the way we did it was just have a moving window that goes from top left all the way to bottom right, and you classify them one by one. So the question is, do we really need to go and make a RetinaNet or faster RCNN to do this, or is there other ways of dealing with this? So one other thing I noticed, so this is the same image that I showed, is just the multiple frames. So every snapshot of a Sapphire imagery is a sequence of 6 frames that's collected from the same thing. So you notice that the stuff that you're interested in, these 4 Annie clusters, are stationary and everything else is moving. So the question is, can we use this motion to filter out this? So just as a first step, we figured that we don't really need AI to do this. It's just a classical image processing. You try to do some filtering and bitwise comparison operation between the thing, and you can recover what you need. But of course, the situation is more complicated than that. There are cases where there is a lot of noisy things that also happen not to change across the images, and that's some avenue for future improvement, but it hasn't been implemented. Okay, so that was the sort of the summary of the paper. There's a lot more in there. Again, please have a look if you're interested. Okay, so now I'm getting into the image synthesis and maybe reinforcement learning. So we'll see where that happens. Okay, so again, I won't have time to go through the details of this, but the idea is what we want to do is to have some kind of an image generator that generates the images similar to what you saw, but is coupled to an orbit propagator. So you can have your satellite move around, and then you have a star database that tells you where the stars and RSOs are located. So through a coordinate transform, so you want to basically be able to point your satellite in any direction and then generate images that are consistent with the reality of that image. And so you will generate a background separately. So these are all the stars, and then you generate a foreground, which is the position of the satellites in real time. And the idea is if you're successful in this, you can close the loop and do any sort of AI analytics in a way that allows you to do a bunch of different things. So this is some preliminary results that they have. So these are all fully simulated. Excuse me. These are fully simulated images with very realistic amounts of noise and bias. Even has these sort of CCD lines that happens in real astronomical images. So it's not dynamic yet, but we have this sort of interactive thing where you can try to play around with different aspects of the image generation and to see what you can see. So the next step is to basically be able to move the satellite within the star sort of scenario and see the streaks and all those things that you saw in the previous images. Yeah, so this is basically what I explained. So your satellite is going to have a pitch, a yaw, and a roll. So as you change that, you need to do these coordinate transforms in a way to map the coordinates of the stars, which is in right ascension and declination, and map it to an XY coordinate in your CCD. And there's some pretty standard linear algebra transformation that you do to do that. Okay, so some concluding remarks. So first of all, so some of the applications we are thinking about in using so I mentioned reinforcement learning because I know you guys are very familiar with it, but it doesn't have to be reinforcement learning. It could be anything else. But basically, we want to be able to autonomously detect. You want to set up different scenarios with different objects, maybe in conjunction. You want to schedule. So if you have a bunch of these simulators running in parallel, how do you do the scheduling and collision avoidance? And one of the things that's probably farther ahead than everything else, but I'm kind of excited about is doing some kind of distributed control of multiple of these satellites, because as the number of satellites increase, everybody will be launching these clusters of satellites of maybe 10 to 12. And you want them to be able to do things together in a way that, let's say, cover the maximum amount of area without overdoing or repeating things that the other ones are doing. So, so there's a lot of interesting work to be done there. So I wanted to highlight some of the challenges and then some of the opportunities. So these shouldn't come as a shock, but the stakes are very high. If you spend millions of dollars to launch a satellite, you really don't have the luxury of having your AI not responding well to distribution shift or anything like that. So this is like one major barrier of sending something to space. So the processing power is limited, but I would say that's not, it's very quickly not becoming not a problem, because these low power GPUs are very powerful, more powerful than enough, and they're pretty low power, and I think they'll be fine. And so generally speaking, so this might be a little controversial, but I think online learning is really not desired in space because you can't predict it. If you can't even predict it for games, maybe you shouldn't put it in space. But maybe I'm proven wrong if somebody can do some kind of provably robust reinforcement learning. We'll revisit this later. Okay, so then there are many opportunities. So one of the things that I'm excited about, and I think the simulator sort of highlights, is so simulators, as the way we talk about in traditional, let's say, reinforcement learning, they are not physics-based. So they have the sim to real issues. If you train something in the simulator, you can't really expect, or you normally don't expect it to work in real worlds. But here, if these are physics-based you could make it as accurate as you want. So there is no issue. So you can train everything in a simulator and expect it to work. So that's one big advantage. On the negative side, I mean, the simulators are going to be slower and they're going to be more difficult to develop. But once you do it, then I think you're good. So another couple of things that are very important is that so manual control is actually not possible anymore. So so specifically, for example, for the Canadarm3 project, it's going to be situated near the moon. So the communication is going to be intermittent and it's going to be a lot of lag. So it is a big requirement to have some level of autonomy so that the arm can sort of manage itself in a way before it can be manually controlled. And I guess along the same lines, as you get more and more satellites sort of entered into the orbit, the operators which are typically manually controlling them cannot do that in any reasonable way. So even though it's a very difficult problem, there is no solution but to try to get over that. So these are some of the opportunities. Okay, so thank you very much. So if you are interested, that's a link to our careers webpage. I just want to highlight one of the positions that's currently open that I think many other people in this call might be interested in. So the position is in Brampton, it's in the space robotics, the senior controls machine intelligence engineer. So it's a senior level position, but if you feel you're qualified, please, you can search for it in Indeed or talk to me or somebody from the Brampton office, and we would be excited to chat with you. Thank you very much.
Awesome. Thank you. Fine. Wow. Please join me with a Zoom applause. That was a fantastic presentation. Really,
thank you.
Really interesting. We have for some questions as well. So please, you do have the power if you would like to unmute yourself, and you have the floor. So ask away. Ask if you are taking on any student interns. So that's great. I think that's a good indication that this is really interesting work.
Well, if nobody else wants to ask a question, I will. How do you mentioned the fact that a lot of the GPU and the hardware that you use is prone to radiation. So how do you harden the systems for exposure to radiation? I'm curious.
Yeah, that's not really my area of expertise. I don't actually know how they do it, but I know they exist. So NASA is developing the actual GPUs. I don't know how they do it. I'm guessing there is some shielding involved. Also using low precision, I think GPUs can help with that so that the bit fluctuation doesn't hurt you as much. But yeah, the GPU part wasn't really my part. I don't know. There might be other people on the call.
Understood.
But you can buy basically radiation hardened GPUs now.
Yeah, I would imagine, we do a lot of work with NVIDIA as well.
Yeah.
And I would imagine that you're not the only customer that's probably asking for something like that. So I was just curious just to see how you were overcoming some of those challenges. But in any case, yeah, that's something that I can look at through other streams. Thank you.
All right. I had one question sent over here. It's actually not really a question. It said, would love to hear the breakdown of that onboard learning. So I guess, when you talked about this notion of desiring to not have any onboard learning with things you're sending into space, do you want to maybe break down and talk a little bit about kind of both sides of that argument? I'm sure you've talked to some RL people about what that looks like, but yeah, just want to speak to that a little bit more.
Yeah. So again, that's sort of my personal perspective that because I see a lot of engineers working on their systems that they're sending to space, and there are very stringent requirements that a lot of system engineering, you need to prove that everything is robust. And it's usually with complicated things, it's hard enough to do that even if there is no AI in it. So even just as a simple software that's trying to search or check that a switch is on or off, it takes a lot of work to make sure that's robust to all the possible sort of inputs that it can get. So having worked with some of these RL algorithms, I would say like that would really make me scared trying to put an RL algorithm in space, trying to do things autonomously. On the other hand, I mean, I can imagine like there are cases where you can, you can turn your epsilon or your learning very, very small so that, let's say in space over time, probably maybe the friction between your joints and other things changes over time. And some of these robotic arms or satellites need to stay in space for like decades. So some of those changes could potentially be compensated by some kind of adaptive learning. But I think there's still a lot of work to be done to guarantee that that's safe. And yeah, so that's one of the challenging things.
Thanks for that. Yeah, we've got one more question if there's time here. Someone's checked Kaggle. Looks like it's around 60 gigabytes. Just wondering what type of GPU capacities do you usually use to run these types of models?
Yeah, so the Brampton, I guess that data set is from Brampton, and I believe they use AWS. So in Richmond, we have a cluster of 6 V100 GPUs that we use. Yeah, so I don't think you need a huge GPU. Maybe just a 1080 Ti would probably be good enough. But I mean, if history is any indication, the Kaggle winners seem to be the ones with a very large number of GPU access. So it will probably take a lot of time, but I haven't actually worked with that data set. So like I said, that's a robotics data set from Brampton, which is not sort of our area. But yeah, I would say you can probably get started with not too many GPUs, but if you're planning on winning the competition, you might need a little bit more.
That's a really good way to look at it. Well, all right, thank you so much. I just want to give one more shout out to not only the amazing presenters that we had tonight. I think this has been, some of the best content that we've had all year. But given that this is our last AI meetup of 2020, I also have a really big team, Amii, that works hard every month to find really awesome content and people to come out and share what they're working on. So please join me in sending 2020 off AI meetup wise with a clap for all the people working behind the scenes to make these so great. And